and I will turn it over to Douglas MacMartin. Thank you so much.
Thank you. Good to be here. Well, not in person, but remotely. Sound quality okay? Video shows up?
We're in good shape here. Thank you.
Excellent. Um, Advantage of Zoom, of course, is fewer greenhouse gases involved in flying all over the place to do things. Um, so I'm going to talk about what is variously known as solar geoengineering or solar radiation modification. That's the IPCC term. Solar climate intervention, you'll sometimes see. Um, Solar geoengineering is probably what it's most commonly referred to as. I'm personally inclined right now to call it with sunlight reflection methods because that's basically what we're talking about. Is the potential to reflect sunlight in order to cool the planet. So I'm going to give you basically a little bit of an idea of what that is, spend a bit of time talking about why this is an important subject to talk about, a bit about what we know, a bit about what we don't know, and thoughts for research and how to move forward. And I'm always happy to take questions, although I can't actually see the room, so and I'll probably miss any questions that show up on the chat because I'll be talking. So Paul, I assume you'll interrupt me, and if there's a burning question that needs to be addressed before the end.
Yeah, I'm gonna leave those till the end, and then we'll take them. Thank you.
Okay. All right. Obviously, just anything that I talk about here is actually a result of conversations with vast numbers of people, but I do want to at least acknowledge some of my key collaborators and grad students and postdocs and former grad students and so forth that have been involved in the work. And the broad context here, you may have seen pictures like this. I deliberately use qualitative rather than quantitative. Nothing that I say about reflecting sunlight changes the fact that we have to cut emissions of CO2 and we have to get those down to zero. What I would say is cutting CO2 emissions is not a solution to climate change. That's not a statement that you will often hear. What it is it prevents the problem from getting worse. And it's only when we get to zero emissions that we stop making the problem worse, but that doesn't make the problem better. And it's kind of like if you know that you're going to hit the car in front of you, you should certainly take your foot off the gas. It would be pretty stupid not to. We don't know today how rapidly that's going to happen. You can look at forecasts and people saying when we should get to net zero, but we don't actually know when we will. The next piece of the puzzle in principle is you can pull CO2 out of the atmosphere, known as CDR, carbon dioxide removal. Lots of ideas in that space. The challenge is that they are typically either expensive or can't be scaled up to a sufficiently meaningful scale to make a difference, or in principle, or they have competition for food and water. In the case of things like growing bioenergy crops and burning them in power plant and sucking the CO2 out of the flue gas, for example, if you're trying to solve the problem or address the problem by growing crops, well, we're already using that land for other things. So on top of that, we don't know how much the planet will warm for a given amount of emissions. We don't know what the impacts of a given amount of warming will be. So Paris Agreement, for example, said we should really try to stay closer to 1.5 degrees and definitely below 2. Nobody really knows for sure whether a 1.5 degree warmer world is safe. We don't know future policy. And in the case of the CDR in particular, that technology doesn't really exist at scale yet, and we don't know when it will show up. And so the reality of all of that is we're sitting here somewhere looking at climate change impacts starting to develop. We don't know how much worse they're going to get, and we don't have a guaranteed strategy in place to avoid significant impacts. Different people might have different levels of optimism and hope, but my reaction is that hope is not a strategy. And it's the future of the planet is not something we want to gamble on and just say, well, we hope that everything's going to work out for the best. So that's the broad context. If you ask me what climate policy looks like right now, I'm going to actually put up this old cartoon from the New Yorker and say, you know, there's a little bit of a sense of just saying, oh, well, we have to cut emissions, we have to cut emissions, we have to cut emissions, and the hope that eventually people will listen and cut emissions. And, you know, this is just an example of that. This is from a paper in 2017 that said, oh, if we start cutting emissions now, we'll be able to gradually reduce them to zero. But if we keep waiting, that curve is just going to get steeper and steeper and steeper. Eventually, you have to look at this plot and say, we're not going to keep emissions below 1.5 degrees, or keep emissions down at a level that will keep global mean temperature below 1.5 degrees. In fact, the reality is, it does not look like we're anywhere close to a trajectory right now that would keep global mean temperatures from staying below the 2-degree number in the Paris Agreement. So that's broad context. So what, back up just a little bit about basic physics for climate change, right? So planet gets energy from the sun, radiates energy back to space. Those two arrows, the net incoming solar and the net outgoing infrared long wave radiation radiated back to space, those have to be equal for it to be in equilibrium. So if one of those arrows is bigger than the other, planet has to warm up or cool down until things are in equilibrium. We put greenhouse gases like CO2 in the atmosphere, and that makes it harder for the heat to escape, and therefore the planet has to warm up until the increase in black body radiation causes those two arrows to get back into equilibrium. And obviously, remove the CO2 from the atmosphere, but that's easier said than done. The other option, the sunlight reflection path, is basically says, can we mess with this other pathway and change the reflectivity just a tiny, tiny amount? If you reflected like 0.5% of sunlight, that would take you almost all the way back to pre-industrial temperatures. You're not talking like a big fraction of sunlight. But really important thing to keep in mind, if you warm the planet by adding greenhouse gases and then you cool it back down by reflecting sunlight. So how would you go about doing this? There's a bunch of different ideas. You could do something in space, but that's insanely expensive and not going to happen anytime soon. The idea that's best understood is you put aerosols in the stratosphere. So aerosol just being small droplet or particle, basically small enough that the gravitational forces are small, so it stays suspended with the flow. And the key is to put it high enough up in the atmosphere where the air is stable. So your atmosphere 101, the surface of the planet is heated from the ground because from absorbing solar radiation. Hot air rises, and so that's convectively unstable, and you get clouds and weather and rain and all of that sort of stuff. If you go high enough up in the atmosphere, you reach the tropopause, and above that, the air is heated from the top because the ozone in the atmosphere absorbs some of the ultraviolet from the sun. And so the first layer of ozone gets more of the ultraviolet. And because it's heated from the top, it's stable. So if you put aerosols into the stratosphere, they stay there for over a year, reflecting sunlight. The reason I have a picture of a volcano here, that's Mount Pinatubo, erupted in the Philippines in 1991. And it cooled the planet by something like 0.5 degree Celsius for the following year, because of the fact that among the ash and everything else, it put sulfate aerosols into the stratosphere, about 20 million tons of sulfate. So we know this works, just basic physics. We know the aerosols reflect sunlight, and because nature does it for us every now and then. And so that idea, roughly speaking, would be you fly special airplanes up to the stratosphere, so high up, you release sulfur dioxide or something like that, turns into sulfate aerosols, reflects sunlight, cools the planet. I am 100% confident that that will cool the planet. There's absolutely no doubt. The rest of the effects, definitely some degree of uncertainty. Um, on the other hand, you can bound the uncertainty a little bit and say, look, if there was anything really catastrophic, we would have seen it after these volcanic eruptions. The second most discussed idea is much less well understood and has a sort of different set of problems. I'm not going to spend as much time talking about that, but it's marine cloud brightening. This is a satellite picture of what's known as ship tracks. So each of those lines you see in the picture is a cloud, and that cloud is basically formed by the pollution from the ship acts as cloud condensation nuclei. And so whatever water vapor in the atmosphere then condenses on that and forms a cloud. And you don't need ships to do that, or you don't need pollution to do that. I mean, you could do that by spraying salt. Some of you might have heard of this as well, just in that we are in the process of cleaning up sulfur emissions from shipping. And over the last few years, the shipping emissions of sulfur has gone down, and that may be contributing part of why last year was notably warmer, and the oceans in particular were notably warmer, is from the loss, right? That pollution is a bad thing. On the other hand, that pollution has been masking some of our warming from climate change. So if you go back to this picture, the potential role for either of these methods would be, and the question for research in a sense would be, if we're going to overshoot temperature targets for some period of time, would it be better in some sense of that word to consider reflecting some amount of sunlight in the interim to avoid the risk, to avoid all of the damages from climate change, to avoid the risks of tipping points and so forth. So that's the broad research question. There are three broad problems with this slide. First is the point that I've labeled there as point 2 is definitely cooler than point 1, but it's not the same as point 3, right? So if you, like I said, if you warm the planet with one mechanism and you cool it back down with something else, you don't quite get back to where you started. And that is a challenge because at least for climate change, we can sort of like, everything's gradually getting worse. All we have to do is remove the greenhouse gases or have less greenhouse gases and things gradually get better. And we can use global mean temperature as basically a proxy for everything else. But in this case, if you drew a straight line and said we're going to hold global mean temperature constant, that doesn't mean that all of the rest of the risks are affected in the same way. Second is the time scale of that is potentially long. I said that lifetime of aerosols in the stratosphere is about a year. So if you stop, it's reversible, for better or for worse. You basically go back, warm back up to where you would have been. That's referred to as termination shock. That could be rapid. And the third and biggest problem with this plot is that it effectively assumes that the choice whether or not to reflect sunlight is independent of what happens with mitigation. That's referred to as a moral hazard problem. I think the main reason that this is controversial is that there are people who would say that people feel that this is being proposed as an alternative and an excuse not to cut emissions. And they'll run around saying, oh, we should be cutting emissions instead. My personal view would be, I don't get into my car in the morning and say, should I drive safely or should I wear a seatbelt? I do both. And in principle, that should be the way we make decisions in the climate system as well. But you might then point out, if we were behaving rationally, we've known about climate change for a really long time. If we'd been behaving rationally, we would have been cutting emissions a really long time ago, and we wouldn't be in this situation. So I'm not going to give you an answer on that other than to raise it as a challenge. And I don't know, and nobody knows exactly how this would be perceived. If somebody said, let's go let's actually start deploying. So little tiny bit of physics here. I'll skip over this fairly quickly. I think this is a satellite view of, if I remember right, the Sereshov eruption releases sulfur dioxide gas into the stratosphere. That oxidizes into H2SO4, which some of you might recognize from chemistry as sulfuric acid. That's the same thing as a sulfate aerosol, basically. So you get that combines with water molecules in the stratosphere. You get a little tiny droplet. It gradually grows as more molecules land on the surface. Occasionally, these aerosols will run into each other and grow from that. And eventually, they'll get heavy enough and they will fall out of the stratosphere. That's the basic physics. In the meantime, they'll transport the circulation in the stratosphere will transport them around the planet. It mixes very quickly in latitude and sort of broadly poleward with a little bit of seasonal dependence in the tropics. So that's sort of the broad picture. We have climate models. This is the climate model that I run is CESM WACM. So this is takes like 10 or 15,000 core hours per year of CPU, year of execution. And this is just illustrating the black dots on the right are measurements taken after the Mount Pinatubo eruption of the aerosols at different locations. The red is the model showing that it broadly matches the observations we've got. On the bottom is just showing the ozone hole over the Antarctic that was caused by CFCs, chlorofluorocarbons and other things. Montreal Protocol in 1991 phased that out, and the ozone has been gradually recovering, and the model captures that reasonably well as well, which is all just to say it's a model, it's not the future, but it is validated against data to the extent that we have data. If you make a forecast with that model of what would happen if you were to deploy stratospheric aerosols, this is basically the suggestion that this could reduce risk. So the top left is just a map of what temperature looks like if you allow the planet to warm relative to today under one of the IPCC Intergovernmental Panel on Climate Change emission scenarios, sort of a business as usual that looks, well, not business as usual, but a scenario that looks broadly like current national emission pledges to reduce emissions. So it'll warm by some amount. On the right is the changes in precipitation, where it's gray just means that there's no statistically significant change. And then the bottom is taking that exact scenario, assuming the emission scenario doesn't change, and adding in enough stratospheric aerosols to hold the temperature to today's levels. And broadly speaking, I'd say it's pretty hard to look at those maps and conclude that the upper panels are less risk than the bottom panels, right? So if you look at climate model projections, and you can run this in as many climate models as you want, it sure looks like we would reduce temperatures everywhere. That means we would reduce impacts that are driven by temperature. We might get some slight shifts in rainfall, mostly over the ocean. And most of the precipitation changes would not even be statistically significant. It's not saying the models are right, but that's basically saying where we are right now on research. If the only thing you looked at is physical climate impacts, you'd roughly conclude that we ought to be deploying some amount of stratospheric aerosols in order to reduce suffering. Okay, so what do we know? We do not have the airplanes right now that could loft enough of a payload up to the stratosphere. As a former aerospace engineer, others have looked at this as well. It doesn't look like it's fundamentally hard to do. Not too many countries could do it, so don't expect some billionaire to run out and go do this. They can't. Not even clear a country like India could go do it. But it's not fundamentally hard. We know it would cool the planet. Lots of climate impacts depend on temperature. There's a caveat there on the sea level rise that the contribution to sea level rise from Antarctic uh, is a little bit more complicated to analyze. There are ways that you can deploy that would definitely be a net benefit, but there's other ways you could deploy that actually are less obvious. Clearly would reduce heat extremes and things like that. It does not exactly compensate for precipitation. That means that if what you are asking is what would this do to drought or what would this do to agriculture, it's slightly less clear exactly what the impact would be. People have looked at many of those things, but there's a lot of impacts that people have not yet looked at. Outcomes do actually depend a little bit on where you do it. So I will say a little bit more about this in a minute, but one of the differences with climate change, we just add CO2 to the atmosphere. And if you want to project what the effects are, that's what you're stuck with. Here you actually get a choice of where you could put them in at the tropics, you could put them in at high latitude. Those will affect the climate system differently. And there are other impacts if you use sulfate aerosols. The reason we talk about sulfate is because that's what volcanoes put in, that volcanic eruptions put in. And so we know a fair amount about what happens when you put sulfate into the atmosphere. We have ways of calibrating our climate models. Sulfate's not perfect. It does interact with ozone. Honestly, I think it doesn't look like those changes would be very big. What goes up comes down, so it comes down as acid rain. And it doesn't just reflect sunlight back to space, it scatters it in all directions. That changes what fraction of the light coming to the surface comes as direct light versus the diffuse light coming in from all directions. And so there's some subtle things like this that make it a little less clear that it's not just a matter of reducing temperature. You have to look at the whole body of impacts. Broadly, what I would say is much harder is thinking about the human dimension of the problem. And that first bullet is really an understatement. So if you were to deploy this, it affects everybody on the planet. How do you go about making decisions about that in a way that is broadly legitimate and doesn't create more problems by leading to conflict, right? Like country A decides to deploy, country B has a drought the next year, it's going to get blamed on this, whether there's any physics behind that or not. I mentioned the moral hazard. I mentioned the termination shock if you stopped right away, stopped very abruptly. And I'd say, these things we're working on these, but the research effort is still, by and large, mostly in the developed world, mostly running Earth system models and looking at the climate response and less on things like ecosystem. And it's been a lot more somebody being interested in particular subject and looking at it, rather than sort of being a much more comprehensive, how are we going to get to a... So if you are a policymaker, what do you want to know? You want to know what would happen to everything we care about. How does those answers depend on how it's done, like latitudes of injection and how much cooling, and how do those compare with not deploying? Same thing on uncertainty, and I think here uncertainty is a bigger deal in a way than it is with climate change. With climate change, like, we got to cut emissions. Even if our models are off by some amount, we have to cut emissions. Whereas here, I think there's a little bit more of a question of maybe there's some realizations of uncertainty that you would choose to deploy and other realizations of uncertainty that you would not. So that's a big question. But by and large, if you're really worried about uncertainty, it's probably a lot safer. Like, I'm a lot more confident in what the planet's going to do if you keep the temperatures not that far from range in which we have some experience. And I have a lot less confidence in what the planet might do if you allow it to warm to levels we've never seen before. You need to understand a little bit about what a deployment might look like, just to answer those. And I'm not a social scientist, so I'm just going to lump the entire social science dimension into one question, which is ultimately that's like, how do you how do you increase the odds of making reasonably good decisions in the space? So that's sort of broadly what you want ultimately as a policymaker. And I'll just, I'll emphasize this. I think I said this. This is different in a way from climate change research. And ultimately, this slide is the reason why I'm sitting in an engineering department and I'm working on this subject, as opposed to it being purely in atmospheric sciences. And that is that we get to choose where you put the aerosols. And so there's a design element of what happens depending on where you put them. And we get to choose how much you put in. And that's not just a matter of saying, like, would it be better if I cooled a little bit or cooled a bit more? But that's also a choice you can revisit every year. The flip side to these is, people are very worried about trade-offs. The fact that not everyone is likely to agree on a deployment. You can't look at that question without taking into account the fact that different choices of where you put the aerosols into the stratosphere lead to different trade-offs. And people are very worried on uncertainty, but you can't think about uncertainty without recognizing the potential to adjust your injection rates. And so just as an example, if we were wrong about, I showed you the slide of the aerosol microphysics. If we're wrong about how big the aerosols get, and so how much time they spend in the stratosphere, that if I just said, I'm going to put, X teragrams of SO2 in the atmosphere and see what happens, that uncertainty would affect how much cooling I got. But the reality is, you can see how much cooling you're getting. And so the reality is, over time, you would put a little bit more or a little bit less injection in. And so what that uncertainty really does is it has no effect on how much cooling you get. The only thing it affects is how much injection you need to get that cooling. And downstream things like how much acid rain you get. The final comment on what's different here is, if you think that people might be interested in asking questions about should we deploy this in a decade, that's a really short period of time to do a heck of a lot of research that we haven't done. And so trying to figure out how to get all of that research done urgently is a really big headache. I'm going to skip that. So if you're thinking about risks and you want to say, I'm going to weigh all of the impacts and risks associated from climate change against all the impacts and risks of SRM, of sunlight reflection method, solar radiation modification, there's broadly, I'd say, 4 things to pay attention to. From on the left, sort of the purely physical. What are the physical effects from sort of a broadly responsible and well-designed deployment? That's essentially what virtually all of the research has been in to date. On the right-hand side, there's conflict, which I'm not even sure I know how to do research, but that's at some level, if this led to a nuclear war, that's by far the biggest impact. So there's ways in which, the stuff is to do the research on, and the stuff on the right might be the biggest risks. So that's I just want to note that. The other thing I would say about uncertainty is, and this is again putting my engineering hat on, I have been involved, in addition to this, I've been involved in the design of the 30-meter telescope ground-based optical observatory. I have a little tiny role in that project. One of the things that engineering project does, and virtually every large engineering project, is they have a risk register, and they keep track of all of the things that could possibly be wrong, and they look at them and say, well, what's the odds of being wrong about this? What's the odds of being wrong about that? What are the consequences of being wrong? And if you find yourself with any risk up in this upper right-hand quadrant, that's the stuff you really need to be paying attention to and saying, we need to figure out how to either improve our knowledge or figure out strategies that make us less dependent on being wrong about that. That's the sort of thing that we just haven't done, right? So I can run a climate model projection and I can say, here is a map of what I think the temperatures would be. What we have not done is things like say, how wrong could our model be and still be consistent with the observations we have from volcanic eruptions? And if it was that wrong, how much would that affect the projections from it? So I have my own guesses that a lot of those things probably don't matter all that much, but they're just guesses, and nobody should make a decision because Doug said, oh, I think it's okay. So just highlighting, we do have a paper from a few years ago that made some attempts to, like, you know, take different risks and figure out where we uncertainties and figure out where we thought we might put them in this sort of a diagram. But they were basically me and Ben, you know, looking at the literature and going, making an educated guess and saying, I think we know a fair amount about this. I don't think we know very much about that. The other thing I mentioned a little bit is just the latitudes of injection. We've been looking with in our group here at Cornell of like, well, okay, you can put them in anywhere on the planet. How many degrees of freedom do you really have? How different are the climate states that you get? What I would broadly say is you can put aerosols in the tropics, you can put them in at the mid latitudes, you could put them in at high latitudes. High latitudes, by the way, it makes sense to put them in the spring, maybe partly because the lifetime in the stratosphere is smaller, but also you only have a lot of sunlight in the summer to reflect. Other than that, it doesn't really matter when you put them in because the lifetime is long enough. And the short answer would be don't put it in one hemisphere because that'll shift the intertropical convergence zone and change tropical precipitation. If you put them in primarily in the tropics, you have more aerosols in the tropics, you have more sunlight in the tropics, you'll overcool the tropics relative to the poles. If what you care about, if you're in India and you care about heat extremes, that's probably the right thing to do. If you put it in at high latitude, you will put more of your emphasis in at high latitude. So if what you are worried about is Arctic sea ice and permafrost and the melting of Greenland and Antarctic ice sheets, you probably want to put them in at high latitudes. Reason I say that's simpler to implement is that the tropopause, the boundary between the stratosphere and the troposphere, is a lot lower at high latitude. And so you could actually start doing that, start at very small scale, but you could actually start doing that today, like almost literally today. If you have a spare, a few $100 million lying around in your wallet, just go buy some Gulfstream aircraft, business jets, and start flying sulfur dioxide up to the stratosphere at high latitude. They can get high enough and you will cool the planet. Please don't go do that. Somebody will probably call me and ask me what they should do, and I would probably say, go shut that activity down. They shouldn't be doing that right now. And then you can put things in, instead of just putting them in at one latitude, you can put them in at multiple different latitudes, and you can use that to sort of try to like balance various different objectives. And then this was just to show this was a case where we were cooling the planet by a little over a degree, and in almost all of the planet, you basically almost, right, like you warm a climate with CO2, you cool back down with the aerosols. If you're careful about where you put them, you do not get back to where you started, but where you roughly get back to where you started, so that the differences are pretty small compared to natural variability. So all the stippling there is basically saying places that you would not be able to tell with one Earth in 20 years whether the climate was any different from the reference climate. I would like to leave my personal reaction, I can't see the room, so I can't actually see people's questions. My preference is to leave lots of time for questions, partly because I tend to give very long answers to questions. But I'm going to leave you with just a few thoughts. first, just suppose we do, I didn't want to make clear about where we might be headed. Right now, all we're doing is modeling and observations, maybe some small experiments, try to ultimately get to a point where one makes a decision. My guess, nobody's going to decide to go do anything as long as climate change looks kind of like, yeah. Whoops, I've been still too long, my lights went off. All right. If climate change starts looking more severe, you start by putting some aerosols into the stratosphere. You compare that with climate models. If your climate models are just like, oh my gosh, they're completely out to lunch, you'll probably stop and revisit. And if that matches climate models, then you get some degree of confidence and you proceed. The reason for saying all of that is some people have this idea of, or the image in their head is like, we're going to be faced with a decision and it's like jumping out of an airplane. We don't know whether our parachute's going to work. That's sort of the wrong metaphor because you can't unjump out of an airplane, but you can always just, if you did choose to do this, you can always just ramp up slowly. You can ramp back down. You can gradually ramp up a little bit more. Maybe I'll skip that slide. Again, just to emphasize, climate change impacts are already here, and we have not crossed the 1.5 degree Paris threshold. People will sometimes ask me, well, who's going to pay to deploy this? This picture here on California wildfires in 2020, that campfire cost probably more than a decade's worth of deployment of SAI. If you could offset one wildfire by doing stratospheric aerosols, you'd save money. Arctic sea ice, September sea ice, been shrinking every year. That affects mid-latitude climate as well. Permafrost thawing. What happens if permafrost thawing accelerates? We don't know. This is actually quite an old picture of ice shelf, a piece of the ice shelf breaking off from Antarctic. The ice in Antarctic is held back by floating ice sheets. Those ice sheets melt, and they're stable because right now, we think, because they're pinned to a grounding line. Instant they melt past that grounding line, they become unstable, they fall, all that ice from the Antarctic flows into the ocean, raises sea levels. If somebody told me today that they were absolutely confident that if we get above 1.5 degrees Celsius for any length of time, we will be committed to 3 or 4 meters of sea level rise from Antarctic, my answer is we should deploy. We know enough. So it's a trade-off of risks. So as long as climate change is kind of like, it's not great, but we can live with it. We think we might be able to solve it. I don't think people are going to deploy this. But I would expect myself that sometime within the next decade, somebody is going to say, oh my gosh, climate impact X, terrible, we need to go do something. And I would like to say that we get the research done now before we're facing the really hard choices. Like a decision whether or not to do the research is comparatively easy. I think I pretty much said everything on this slide, other than to say back to what I said near the beginning, the single hardest part in this whole thing is how do you make decisions and who makes those decisions? I think that gives us lots of time for questions. There's lots more things I could say that I haven't said, but I might pause for questions. And
I'm going to see if
I see one on Zoom land. I don't know about the room.
I'm going to try to see if we can shift the view to allow everybody. No, that's not that. Could you stop sharing, Douglas? Maybe
Yeah.
difference.
Yeah, I do have a question. I don't know how to use the chat, but
go ahead with it. Just speak out. Go for it.
Yeah, so I'm curious, would it be possible to deploy like sulfates via just having sulfates in like jet fuel or something like that, wouldn't that make it a little bit cheaper? Like if you could do that.
I mean, I guess I'd say a couple of things. One is cost is not the driver here. If the cost was free, I don't think that would change decision making at all. It's the direct costs of deployment are probably billions of dollars, maybe 10 billion. The indirect costs of deployment, like putting monitoring systems in place, maybe compensating countries that feel like they've been harmed, those are probably much larger. Certainly the geopolitical costs. As a former person who used to work with Pratt & Whitney, the idea, so the answer is you could put sulfate in airplane fuel for airplanes that are flying in the lower stratosphere. Most of those airplanes are not high enough, and so you're just barely getting it into the lower parts of the stratosphere, and the lifetime is not going to be very long. So it's not really the most efficient way. The reason that I mentioned Gulfstream is that business jets have a ceiling that's higher than, say, a 747, and so you're getting at least a little bit higher up. Even there, you can still really only do it at high latitudes.
Thank you.
So
Steve, did you want to, I don't know if I should take questions, or Paul, you want to take questions?
let me just ask for anyone who has a question, just go ahead and shout it out.
Okay. All right. I'm shouting. Thank you, Douglas. I have a couple questions. Number one, is anyone researching the impact of this on photosynthetic activity and crop yields?
I actually have a paper in my inbox to review and a reminder saying your review is due really soon, specifically on photovoltaic. Concentrating solar, the answer is pretty clear, right? If you reduce the direct sunlight by 5%, you reduce concentrating solar by 5%. Solar photovoltaic, because it can use diffuse radiation as well, it's more a matter of the total sunlight that's reduced, which is only like a fraction of a percent. And it turns out that I'm not an expert in this, but the efficiency of solar PV goes down with temperature. And in most of the world, that's actually a bigger effect than the loss of sunlight. So in most of the world, it actually is a net benefit for solar PV, which is a bit counterintuitive.
Yeah. And what about crop yields, photosynthesis?
Crop yields, again, it's a little complicated. Typically, the upper layer leaves are saturated with light already in most plants. So if you reduce the direct light, it doesn't really do much. If you reduce it a little bit. If you reduce it too much, it has a big effect. And then the lower leaves are getting their light more from the diffuse radiation. And since the diffuse radiation is going up while the direct radiation is going down, in principle, you would expect net photosynthesis might go up.
Huh.
But some tricky questions there, right? Of like, well, now maybe the light's getting to the weeds.
Yeah.
Right, so you might actually be, in the long run, having some slight changes in interspecies competition. That's a valid question that we don't really know the answer to.
So
I have,
oh, all right, fine. Go ahead, Nikki.
it's sort of following along your lines, Steve. I'm concerned about the sulfuric, the acid rain coming down, and also concerned about the geopolitical implications. And how do you, this is going to cross all country lines, and do all countries want their lines crossed? So.
Yes. Right now, we put close to 100 million tons a year of SO2, sulfur dioxide pollution, into the troposphere. That is actually offset. It's masking some amount of global warming, and we're not quite sure how much. It might be masking a significant amount. That's bad for air pollution. It's bad for acid rain. But the lifetime in the troposphere is so short that the amount that you would need to add to the stratosphere is, if you added like 10% of what we're currently emitting to the troposphere, that would probably cool you all the way back, almost all the way back to pre-industrial. So it's not a huge fraction in the net, although it's a little more complicated than that, because right now you put pollution up and it comes down mostly over populated areas. Whereas if you're doing this, it comes down much more broadly distributed, which means comparatively the health impacts would be less, but you might also now be putting acid rain in places that were previously fairly pristine. So that's.
I mean, I remember that, back when the 50s and 60s, I mean, we were having a lot of problems with acid rain, and now you're talking about acid rain, and it sort of raises all sorts of concerns.
Yep.
And also, I thought the ozone hole was growing again.
There is variability in that, but broadly, I mean, the broad trend in the ozone hole is in the right direction. There was some uncertainty because emissions of CFCs are not as low as they're supposed to be. I guess my broad answer to everything would be I think there is absolutely no question that we would rather not be in the position we're in. We would rather that CO2 emissions were zero because we had been addressing the problem in the past. And the challenge in some sense is this is terrible. I don't think anybody would say we want to be viewing this as a alternative to cutting emissions, but it may still be a lot less risk than allowing the planet to warm if there's a way of managing the politics that avoids it being treated as an alternative. And then the geopolitical questions, I agree. I have no idea. Again, if the consequences of not deploying become really, really stark, that might be the situation in which the geopolitics are not that bad. But if somebody decided right now to deploy, I think there'd be a pretty horrible backlash, and I think rightly so. But yeah, I don't know how to solve that. Other than to make sure there's adequate research on the table, so that at the very least, all of the countries are looking at the same set of information about what they think will happen.
So basically what you're trying to do is to get the science in place so that if we have to pull it in, we can, and we would have the facts behind it.
Yeah, and even whether we pull it in or not, that we can make those decisions in a reasonably informed way, and ideally in a way, the only way that I know how to get at either the moral hazard or the potential for geopolitical conflict is to make sure that there's a reasonably robust set of scientific knowledge on the table. So on the moral hazard side, if you can really clearly lay out, look, these are the benefits, these are the harms, this is not a get out of jail free card. It would, the acid rain is a real thing, these other effects are real things, we have to trade those off. That might at least mitigate a little bit against any tendency for the moral hazard. And then again, if every country in the world sort of says, oh yeah, we can see that would reduce our temperatures, we agree that it's not going to have catastrophic impacts in our country, maybe that's at least a little bit of a way to mitigate against that risk, but I don't, it's not going to solve it.
So
I'll let you go, Paul, because I have more questions, but that's all right.
Sure, thank you. I appreciate your question. That's a good one. So I have two questions actually. One is, as far as we know today, can this be done more or less sort of indefinitely, or do we know if this were done for 100 years, 200 years, would that just continue with the same physical effects that you've described? And then secondly, as I understand it, it's going to reduce the heating from carbon dioxide, which is of course the main effect. But there would still be the excess carbon dioxide in the atmosphere, just wouldn't be having the heating effect. are there other effects of carbon dioxide that we need to care about in that context?
Yeah, so the second one's easy. Acidification. Right, so the CO2 in the atmosphere makes the oceans more acid because the oceans uptake that CO2. The first one, I would say, there's nothing in the physics that says you couldn't just do this forever. That's more a question of the geopolitics. And you do, the only thing that sort of keeps accumulating is the acid rain effects. Gradually, that's sort of like the only cumulative type issue. That said, it's hard to project technology 100 years in the future. If somebody were going to deploy this in 10 or 15 or 20 years, they're probably going to use sulfate because that's what we understand the best. If somebody has been deploying this for 100 years, the odds that they're going to stick with sulfate, probably switch at least to something like calcite that wouldn't cause the acid rain. Might even invest in space-based stuff that, in the long run, then you don't need to keep maintaining it. So I'd say, the real issue on the indefinite is more the political challenges associated with, how do you build confidence that you could maintain this for a really long time?
Thank you. Steve?
Do I get to ask 2 questions too?
Go for it.
So I've heard about a plan or a strategy to increase albedo from the surface using mirrors.
Yep.
And presumably that's reflecting more on the UV side than on the infrared side. But is, based on assuming that we could do this on enough surface area to make a difference, is it in fact would it have the same impact, the same effect as aerosols in the stratosphere? And the second question, at the very end of your presentation, you said, if climate change goes haywire, you would say deploy today because we know enough. We know enough from volcanic eruptions, or have there been pilot studies that maybe haven't made the popular press? I mean, how do we know enough to deploy now?
Okay, let me do the first one because that's easy and the second one's hard. Sure, you can reflect the sunlight off from the surface. Pretty much has to be in the visible because that's where we get the energy on the surface. That's why we can see in the visible, right? Although you can also play in principle with increasing the outgoing radiation, so increasing emissivity. The challenge is if you wanted to cool the planet by, you want to be reflecting a fraction of a % of sunlight, the continental area of the US is like 2% of Earth's surface. So you're talking about putting mirrors over something that's a significant fraction of the area of the US, if you actually want to affect global temperatures. So I'd basically just look at that and say it's bonkers. That said, you might be able to do something regionally and say, okay, well, in this particular region, it's important to reflect sunlight, certainly like for urban heat island. The other challenge, and this is an issue with marine cloud brightening as well, is if you put a large forcing over a small area, that's going to have much more substantial climate effects than a relatively uniform forcing. So the stratospheric aerosols in a way sounds the scariest of anything because you're putting, well, literally sulfuric acid in the stratosphere. Very, very dilute. But from a climate perspective, that forcing is now much more uniform in space, which has a big advantage relative to focusing it on smaller areas. In terms of the pilot studies, I'd say no, and the challenge is that most of the uncertainties that one would like to resolve, I'm not convinced that you can resolve with a pilot study. That is, right, we have volcanic eruptions that put 10 or 20 million tons of sulfate in the stratosphere and observations of those that help us calibrate the model, at least of how the aerosols move around the stratosphere. It seems really hard for me to believe that an experiment that releases like even a few going to teach us much that we don't already know. And then in terms of like how the atmosphere responds, that's not stuff that you can actually tell experimentally without actually deploying it. So the only way to actually figure that out is to project it with a climate model. And then, you know, is that more or less risk than climate change? The reason I would personally say that you can make an argument that that's less risk than, say, allowing AMOC to shut down or allowing a few meters of sea level rise would be the fact that it's not a static decision that you have to accept. You could always try a little bit and ramp back down. And so it's sort of in that sort of idealized physical world where you don't have political processes that push you to sustain things that shouldn't be sustained and that sort of stuff. So really answering that question is actually a hard question.
But you're still confident that we know enough.
If I would say, you know, when do you know enough to deploy? Depends at least as much on what the consequences of not deploying are as what you know about deployment, right? So if you ask me today, should we deploy right now? My answer is no. But if you ask me, if you said, if we don't deploy, we are going to have this absolutely catastrophic impact on the climate system, should we deploy? My answer would be, sure, we can always start small and we can always ramp back down if we see something. Right, so I guess what I really mean is that the question of when do we know enough is not a straightforward question to answer, simply because it's not just about the consequences of action, it's about the consequences of inaction as well.
I'm going to say it's Nikki's turn now because it's her turn.
And I'm just curious about feedback loops. So if we put the sulfur into the stratosphere, would that stop the feedback and the tipping point for the peat melting and releasing the methane that it's releasing right now? Or is that one of those things that would continue because it's already in a feedback loop? And it's generating its own heat, so to speak. And I don't know how much that's relying on the sunlight heating or if it's just that it's generating heat, that kind of thing. So is there any the thought about the glaciers melting, the peat melting, that kind of stuff?
There might be some localized places that I'm not aware of where that internal self-generated heat matters, but at least for permafrost as a whole, yes, this would break the feedback loop. Nothing else, right? Like the permafrost refreezes every winter. I mean, the non-permafrost, right? And so that you do break.
But that's the problem. It's not right now.
Well, even the parts that are thawing, they're thawing in the summer. Right, so the perma and permafrost is basically the part that's frozen all year, and so now it's no longer frozen all year, but it's still frozen part of the year. So you're still getting into that frozen state. Broadly, the same with Arctic sea ice. Arctic sea ice is essentially should be reversible. It's reversible every season. We grow the sea ice every winter. It's just we're melting too much of it in the summer. So if you reflected a bit of sunlight, you would stop that one. Of course, any carbon that's lost to the atmosphere from permafrost, you're not recovering that, but you do stop future thaw. The ones that are less obvious, the AMOC, the Atlantic Meridional Overturning Circulation, if you acted before it hits its tipping point, you can probably stop that from shutting down. If you wait until that tipping point has started, it is a true bifurcation, and it's too late. And the same with individual ice sheets, ice shelves in the Antarctic. Those are basically sitting on top of a grounding line. Once they've melted back past that grounding line, it would take an awful lot more effort to refreeze them out to the grounding line. So once they're past, they're now unstable and they melt all the way back to the next grounding line, and there's probably nothing one can do with that. So there's a few of those tipping points that one would have to act before it. And some of the ones like the permafrost and the Arctic sea ice should be fine whenever. And then some of the other ones that have been noted, like the Amazon dieback, I'd say is actually much more, I think the short answer is knows.
If I can just come in with another question then. So Doug, you've used examples of sort of cooling, maybe like reducing heating by about 1 degree. Again, not that I would suggest this, but just to understand, the physics of it. As if one were to think about adding more and more and more of whether it's sulfur dioxide or whatever it might be, could you do this, for 2 degrees, for 3 degrees, for 4 degrees, in terms of our knowledge of that? How far does that go?
So let me make 3 comments. One is that we don't know of any physical reason right now that would limit you to like 2, 3, or 4 degrees of cooling. But of course, all of the side effects from this would get gradually worse. So, that's yet more reason, and there is more uncertainty. So you may get to a point where the effect kind of saturates and you just can't, you put more sulfate into the stratosphere and it just coagulates on existing aerosols and falls out, and you just can't get more sulfate into the stratosphere. That is almost certainly at least several degrees of cooling before you would get anything close to that. And again, if we really were facing a world that was 4 degrees warmer, then the consequences of not deploying are so catastrophic that of course we should deploy. But that's yet more ammunition to say, don't let yourself into that situation. This is not a substitute for cutting emissions. It's something you add on top. The second comment would be the 1.5 degree number or the 2 degree number in the Paris Agreement. There's are sort of pretended to be connected to impacts and saying, 1.5 is safe. But really those targets came from somebody saying, what's the absolute most that we can even fantasize could be achieved? If you were to actually start deploying and the effects look okay from deploying, maybe you're better off cooling the planet back down to 1 degree or even cooler than that above pre-industrial. I don't know. And the third comment I would make is right now the planet is warming by something like 0.2 of a degree per decade. And you probably don't want to be cooling by more than a couple tenths of a degree per decade. Right? Rates of change are also bad. So you don't want to just suddenly turn it on and cool the planet by a huge amount. And what the upshot of that would be that even after you've been deploying for a decade, at that point, you're probably only cooling by 3 or 4 tenths of a degree at most, maybe less, which is just to say, the hypothetical about should you be cooling by more than a degree, how much could you possibly cool? That decision is much further in the future than the decision of whether to start deploying. And obviously, when people make a decision about whether to start doing something, they want to see projections of what would happen if you were to continue. But fundamentally, it's at some level, the more immediate question is, would cooling by a few tenths of a degree be better than not cooling by a few tenths of a degree? Would cooling by 0.5 degree be better than not cooling by 0.5 degree? And sort of anything beyond that, in principle, you only have to decide that after you've already started, at which point you'll suddenly have vastly more information than we have right now, where we're using model projections only. Like I
So
said, I tend to give long answers to questions.
very helpful.
I feel like it's opening up a real can of worms as to things that we don't know about. If we start cooling and like you said, go down 1 degree, we know what the weather pattern was 20 years ago when we were cooler. But by dropping our temperature back down to that, we don't know if the weather patterns are going to be the same, or if everything has been affected so much that the weather is still going to be pure chaos, even if we drop it down. So yeah, it just strikes me that there's a lot of unknowns that we're talking about here.
Yep. So that basically all has to be, with those choices, and that just has to get weighed with everything else, right? Like I can say pretty confidently that if you cooled by, back down to 1990 levels, we would probably have Arctic sea ice pretty close to 1990 levels. If you said there's a tipping point in Antarctic ice shelf melt, that's the one where I might be worried that, if we've already, if we keep at current temperatures, maybe that's not good enough for the Antarctic ice shelf. I don't know. Nobody does. So that's where the trade-offs get to. But I would agree 100%. The less, if we were to choose to do this, in some sense, the less we need to do, the better. Which yet again, I'm like, yeah, all hands on deck cutting emissions, right? I do feel a little bit like when people ask me what I do and I say, oh, I'm working on this, you could get a little bit of an action of like, wow, if people are so terrified that they're willing to consider insane things like that, maybe we should take cutting emissions more seriously. I'm like, yes. Right? It's like there's a way in which it's actually an inverse moral hazard even to talk about it.
Yesterday we were talking about wicked problems and what they are, and I think this is definitely falls into that category.
Steve?
Yeah, just one sort of random question. You increase, maybe I should know this, but if you increase sulfuric acid concentration in the stratosphere enough, can you influence the production and reactivity of polar stratospheric clouds and exacerbate the ozone destruction problem?
Yes.
No more questions, Your Honor.
Yes. So I'm not an expert on PSCs. I know that they are represented in our climate model. I don't know how well they're represented. You might know the answer to that better than I do. So sulfate aerosols do at least 2 things to ozone. One is they provide surfaces so that the chlorine can go from an inactive reservoir to an active reservoir, right? So you now have a surface for that catalytic photochemistry. So it does, in principle, destroy ozone at high latitudes. It also changes because the aerosols absorb a little bit on the IR in the near infrared, and so you wind up heating the tropical stratosphere, lower tropical stratosphere, and that changes both ozone production and destruction in the tropics, and it changes transport. In the high northern latitudes, the model predictions right now would say that the changes in transport tend to be larger than the loss rate from the ozone the chlorine photochemistry. So that in the high northern latitudes, it potentially leads to an increase in ozone, not a decrease. And in the high southern latitudes over the South Pole, the ozone photochemistry that dominates, and you wind up with a net loss in ozone. But it's kind of like in our simulations, if you started deployment in 2035, the worst case ozone you get over Antarctic is back to 2025 levels, right? So it's kind of like it's shifting the ozone back a decade. And so broadly, my reaction would be, we should know more about PSCs, but I kind of feel like we'd have to be really wrong about the PSCs in the model for it to be a big enough effect to matter. The other observation on ozone, right? The main reason we care about ozone is because of the UV that reaches the surface. And that's actually not just the ozone, because the stratospheric aerosols themselves will scatter some of that UV. And so you actually might have the opposite sign problem of not having enough UV at the surface. So just to say, it's super, super complicated on the chemistry side.
Is there evidence of that from Pinatubo?
There's certainly evidence on the ozone effect, but I think that there's all sorts of things where people will look at and say, "Oh, let's go look at Pinatubo," and it's just like either we didn't have the observations, or the observations are so noisy that you just can't see any signal.
Yeah.
In which case you're like, well, if we can't see a signal with 20 million tons of sulfate. Right. So people, for example, people have said, oh, this might affect cirrus clouds in the upper troposphere. It's like, can't see any signal at Pinatubo. So sure, it might. But
So we need another volcanic eruption, is what you're saying.
what we need.
Go to Iceland.
Yeah. Well, a volcanic eruption, an explosive volcanic eruption, right? Iceland's got the wrong types of volcanoes.
It's now almost 4:15. Douglas has gone well beyond the time that we originally asked for.
But thank you.
Partly my fault, because I answer all these questions with long-winded.
Well, this has been just extraordinarily helpful, in terms of our whole semester-long program. We knew this was a big gap, and I don't imagine we could have gotten someone better than you, Doug, to fill it. So I'm so grateful
Thank you.
for that, and for taking all the questions as well.
Yeah, thank you so much.
Thanks. I'd say you can always send me email if you have another question, but my email tends to overflow, and I don't guarantee that I can succeed in ever catching up. So if it's a burning question, you might have to send me a couple of emails to prompt me. Paul knows this.
Thank you again. Thank you very much.
Thank you.
Thanks.
Okay.
It's been very helpful.
Bye.